Okay, thank you. I'm just going to share my screen now. And please let me know when you can see the slides. Can you see these now? Make well-informed decisions. However, despite advancements in technology and understanding, we are still finding the number of incidences are not decreasing. So, how can we help to reduce, or at least reduce the significance of incidents? One way is to better understand the risks to make better decisions. With a large number of incidents, they begin often with a loss of containment or a release of a hazardous material that has led to the dispersion of a flammable cloud, resulting in a fire or explosion, or a toxic cloud into populated areas. To help us understand the effects of these releases, we have a number of well-established consequence modeling tools, which are continuously being developed. There are analytical tools such as Shell-Fred, Effects, and FAST, as well as computational fluid dynamics, such as FLAX and KFX. Which one to use will depend on what we're trying to understand, the complexity of the scenario, the site, and what level of detail is required. Now, analytical models are great. I love them. They're fast and easy to use, with models running in a matter of seconds. They're very good when being used as a quick screening tool for a well-validated free field release or an unconfined release. As a general rule of thumb, though, they're only about plus or minus 30% level of uncertainty in consequence modeling. What they can't typically consider very well are the effects from obstacles and structures, such as the effects of an explosion pressure reflecting off a large storage tank, or say a high embankment adjacent to a release. So what? What does the effects of an object or structure have on a consequence from a release or loss of containment? Well, here is just a small example to show the effects that geometry of a site can have. Here we have two enclosures of both equal volume with the same mass of propane gas inside and the same outside dimensions. However, the first one on the left has 9 820 millimeter pipes inside to simulate, say, one part of a refinery. And the second has 45 smaller 164 millimeter pipes to simulate another part of, say, the same refinery. It's important to note that they have the same blockage ratio, which is all that you can use as an input on an analytical model. So let's see what happens when we introduce ignition source for the first case. Whoa, that's a pretty nasty explosion. That one there had a peak pressure of 0.02 bar. Now, let's see what happens in the second case with the same ignition source in the same location. Yikes. Hopefully this is coming through for you guys. This one was far more significant and at a pressure of 2 bar. That's 100 times higher pressure than the first case. So, the same volume, the same blockage ratio, and the same fuel. The only difference was the obstacle diameter, but it resulted in 100 times higher explosion pressure. This difference is something that only CFD tools can accurately predict. So, this brings me to CFD, Computational Fluid Dynamics. CFD is nothing new. It's been commercially in use since the 80s and is widely used in industry for fluid flow and heat transfer. But when it comes to consequence modeling, CFD is the only model that allows for describing the interaction with geometry in detail. You see, analytical models represent circular contours, like the explosion overpressure contours in the example on the left, and don't consider obstacles. Whereas CFD will give a more accurate picture of what's happening. If we look at this example, we have a 5 bar and a 1 bar overpressure contour from the analytical model, and the in the green, the 5 bar, and in the blue, the 1 bar overpressure results from a CFD model. You will notice here that the CFD results on this example show a 5 bar overpressure exceeding beyond the 5 bar contour interval from the analytical model. And similarly, here in the blue, a 1 bar overpressure from the CFD model inside the 5 bar contour from the analytical model. This is because of the influence of surrounding geometry not being considered in the analytical tool. Similarly, with the image on the right, which shows a bit more of an extreme example, but shows how much an obstacle can impact dispersion, which would not be able to be captured in an analytical model, where it can if we're using CFD. To highlight this point even further, here are 2 examples of releases with different wind conditions showing the results from an analytical model versus CFD. The red line here and here shows the analytical results, and the blue, the CFD. The results on the left is typically what most people think is the difference between the types of tools, with analytical models being more conservative than CFD. CFD results inside the analytical results. But as you can see on the result on the right, a change in the wind speed only, and suddenly the analytical tool is significantly under-predicting the extent of dispersion. And this is chlorine gas in a city centre, by the way, not some. Now, with only a different ignition source location, as you can see, there was quite a difference between the 2. Here is just a quick example as well of CFD modeling output, which shows 9 different ignition source locations for a one system. Using CFD for this purpose was very valuable when considering target locations of interest, such as populated buildings or offices on site. Of course, it's difficult to predict the ignition location. However, we can be mindful of ignition sources on site, such as vehicle movements through one area. And this can help us, using CFD, understand their impact and assist with site layouts. Just to finish off, before I get onto the case study, here is a quick demonstration to show the accuracy of CFD in predicting consequences. This video shows a side-by-side real-time test of a CFD model against a real example. As you can see, it's pretty accurate. I'm now going to present a case study where CFD modeling was used for analysis to inform the effects from ventilation for the hazardous area classification and for the explosion relief requirements for a hydrogen refueling station. Here is the hydrogen refueling station being considered. Due to its low density, hydrogen, it's necessary to compress the gas to around 700 to 1,000 bar gauge. This is in order to provide sufficient range for typical passenger cars. Compressors are often in enclosed spaces for weather protection and noise issues. And ventilation has often been used as a basis for safety to avoid accumulation of flammable gas in the industry. But how effective is ventilation for a very high pressure leak? Could we really get a zone 2 NE like is common for other low pressure or non-hydrogen systems in the industry? Well, let's take a look. For the system, the compressor for the refueling station was located in an enclosed space to the right of the module shown here. The main problem we faced is if there was a leak, there would be dispersion of flammable gas and a potential for a subsequent explosion. What do we want to know that CFD modeling can tell us? Is the ventilation provided sufficient to dilute the hydrogen leak below the flammable limits? If there was an explosion, what overpressure can be expected? Can the consequences of an explosion be mitigated using explosion relief panels? So let's find out and start with defining the worst case credible scenario. In the compressor module, leaks were expected to occur at the joints and instrument connections associated with the compressor. This image shows the location of the leak that was used in the study, which was on the discharge side of the compressor with 100% hydrogen at 950 bar. And the leak was pointing vertically downwards, selected as the most likely worst-case scenario. Vertically downwards was selected because there will be a high momentum from the discharge, and this will be partially destroyed when it impacts on the ground, causing the leak to spread at first and only then start to rise towards the extraction point. The scenario had a 30-second leak duration as defined by the process safety time calculation from the gas detection and shutoff system. 2 hole sizes were used, 0.1 and 0.5 square millimeters, as described in IEC 60079, to represent a release and the conditions where the release might expand, as is the case with high-pressure leaks. Within the compressor module, there were 3 grills. There were 5 grills, 3 on the front and 2 on the back, all at ground level, with the extraction vent at the roof with 1,000 cubes an hour of ventilation rate. Now, before we get into the CFD modeling, I just want to benchmark against IEC 60079 bar 10 by 1 for the system which gave a ventilation velocity required to achieve high dilution as being 17 meters per second for a 0.1 mil squared hole, and a very large 85 meters per second velocity for a 0.5 square mil hole. Just to note that these velocities are required around the leak points, not just in the general area. Such high ventilation velocities needed to achieve high dilution for a non-hazardous zone or a zone 2 NE is just not achievable. It's more likely the 3-meter zone 2 would cover the whole enclosure, which is reasonable for a system such as this. But what could CFD modeling show us? Well, let's take a look at some of the results. This is the results for the original system for 1,000 cubes an hour ventilation rate. The legend here shows a ventilation velocity of 0.1 meters per second in dark blue, up to 15 meters per second in dark red, and the red circle in the corner indicating the location of the release. The results from the CFD model show that the original system, the ventilation velocities at the release point, only 0.5 meters per second, a long way from the 17 meters per second required for high dilution. Also note that there are areas with even lower velocities, shown by no color, indicating ventilation dead spots. With CFD modeling, we can easily set up sensitivity cases, and we did this to compare different ventilation rates. The original 1,000 cubes, 5,000 cubes, and we even went to 10,000 cubes. The effect the ventilation rate had on the hydrogen concentration following a release. The legend here shows concentration of 2% or half the LFL in dark blue, up to 81% in dark red. As you can see, the original 1,000 cubed an hour and 5,000 cube an hour ventilation rates, they're definitely resulting in a flammable atmosphere. However, for the 10,000 cube an hour ventilation rate, the hydrogen concentration is around between 2 and 4%. Much better than expected on defining the velocities based on 60079. Although this is still borderline, and you would still not consider ventilation as a safeguard, it does, however, highlight how CFD can give a much more accurate information than relying on the conservative values that are given in the standards. But let's take a step further and look at the dynamic simulation. Here are the results from the flammable gas cloud size within the container against time for the different ventilation rates considered. This graph shows that the maximum flammable cloud size was reached over the 30-second leak duration, but also shows how long it took for each case before the flammable atmosphere was removed. For the original ventilation case, this lighter color here, it was more than 80 seconds before it was reduced down over the 30 seconds. However, this is much greater than expected. This is the time accelerated results for the flammable cloud within the container for the 1,000 cube an hour ventilation rate. Hydrogen fills the container during the 30 seconds release and then is slowly extracted by the ventilation system over a minute after the release has stopped. Again, this is time accelerated just for the presentation purposes. And then if we compare this to the time acceleration results for the flammable gas cloud within the container for the 5,000 Q ventilation rate, you can see that the hydrogen still fills the container, but it is extracted much faster, only 15 seconds after the release stopped. And of course, for a bigger leak size, we can see here that it took over 20 seconds to reach the maximum cloud size for a 0.1 release, 0.1 mil squared release, but only 10 seconds for a 0.5 mil squared leak. And also note that the flammable volume decay for the larger leak took much longer, reduced to 0. Of course, this is not unexpected given the larger hole size, meaning a larger flammable inventory. For this case study, we also then want to look at the overpressure generated by an explosion and the benefits that ventilation had here as well on the explosion relief from the enclosure. The aim of the explosion relief is to control the maximum overpressure within the enclosure by allowing the overpressure to relieve externally in a controlled manner. We use CFD modeling to predict the effects of different ventilation rates had on the overpressure value. This plot here is a comparison against the original ventilation rate, showing the reduction in maximum overpressure as a ratio of the original value. And as you can see, there is a significant decay. With 2 times the original ventilation rate, there's a 20% reduction. And with 5 times, giving it 80% reduction. And with 10 times, it's within the panel yielding value. This relates to time for the reduction of the flammable cloud size shown in the previous slides, where 2 times still took significantly longer than the 5 and 10 times scenarios, which is as expected.
Excuse me, Mr. Hawley, time is up.
Yes.
Maybe you can continue directly to conclusion. Time is up, Mr. Hawley.
Okay,
so,
sure.
Yeah. Maybe...
I've got 19 minutes on mine, but okay, sure, no problem.
Okay, thank you. Okay, Mr. Hawley, can you hear me? Hello?
Yes.
Yeah, okay.
Hello.
So maybe you can go to your conclusion in your presentation, because time is up now. Okay.
Oh, yes, beg your pardon. I thought you wanted me to stop presenting, so I've shut that down. I will share screen again.
No, I mean, I just supposed you to go move forward to your conclusion.
Okay.
Yeah. Okay, you can sum up your presentation, please.
Sorry, I closed it down thinking you were asking me to stop.
Mr. Hawley?
Yes.
Okay, maybe you can share again about your... Okay, and now move to your conclusion to sum up your presentation, please.
Sure. Well, basically the conclusion from the case study was that CFD modeling was able to provide a much more accurate understanding of the system behavior to help inform design decisions. It provided a dynamic model against time to give an understanding of the sensitivities of the system for different ventilation rates to help with the cost-benefit analysis and also potential large justifications. And it revealed the consequences from the system that weren't anticipated by the design team, which I had on my previous slides. But that's it. Thank you very much.